Hey everyone, and welcome. Today we are diving deep into combinatorics. Now, I know that word can sound a little intimidating, but think of it this way. We're not just going to memorize a bunch of formulas. Instead, we're actually going to build a powerful toolkit. By the end of this, you'll have a set of mental tools ready to go, turning those complex counting problems into clear, solvable challenges. So what do you say? Let's grab our hard hats and get to it. Okay, so to kick things off, let's chew on this question for a sec. How many ways can you represent the number 4 as a sum of positive integers? At first, it seems pretty straightforward, right? We're just adding numbers up to get 4. But how many ways are there, really? This is a perfect little example of how counting can get real interesting real fast. Go on, give it a thought. How'd you even start? And there they are, all 8 ways. Now, what's interesting here is that order matters, right? 1 plus 3 is a different beast from 3 plus 1 in this case. Now imagine trying to do this for a number like, say, 20. It would be an absolute nightmare just listing them all out. And that is exactly why we need a better way, a system. And that, my friends, brings us to the official definition. Combinatorics is basically the art and science of counting smartly. The whole goal, every single time, is to find an efficient, elegant formula so we don't have to just brute force the answer. It's all about finding the underlying pattern, the hidden structure, and grabbing the exact right tool for the job. All right, so here's the game plan. We're going to start with the most fundamental tools for choosing things and distributing things. Then we'll learn how to deal with those tricky problems where things overlap. We'll even take a quick peek at some advanced tools. And finally, we'll tie it all together with a summary that's going to be perfect for your exam prep. Let's get building. Okay, let's dive into our first tool. This is the big one, the absolute bedrock of so many counting problems. It's all about choosing subsets. And the main hero of this story is the binomial coefficient.
You're going to see this notation everywhere, I promise. It's read n choose k, and it's asking a simple question. If you have n distinct items, how many different groups of size k can you make? And here's the absolute key takeaway. Order doesn't matter. I'm going to say that again. Order does not matter. A team with Alice and Bob is the exact same team as one with Bob and Alice.
Okay, I love this slide because it shows you 2 totally different ways to think about the exact same problem. And for an exam, you really want to get both. The recursive formula on the left is all about logic, right? You pick one special element. Either it's in your group of k, so you just need k minus 1 more from the remaining n minus 1 people, or it's out of your group, which means you still need to pick all k from the remaining n minus 1. The factorial formula on the right is, well, a bit more direct. It's like, let's find all the possible ways to line things up, then just divide out all the internal shuffles we don't care about. Think of these properties as your secret weapons, your cheat codes for simplifying tricky problems. That symmetry one is so cool and intuitive. Choosing 3 people for a team out of 10, it's the exact same math as choosing the 7 people you're leaving behind. Mind-blowing, right? The summation property tells you that the total number of possible subsets of any size is just 2 to the power of n. And yeah, of course, these are the famous coefficients you see when you expand something like a plus b to the nth power. And check this out. Pascal's triangle is just a beautiful visual way of seeing that recursive formula we just talked about. See how each number is just the sum of the 2 numbers right above it? It's awesome, not just because it looks cool, but because it's a super fast way to calculate those smaller n choose k values on the fly. All right, tool number 2 for our toolkit. We've got a handle on choosing things, but what about distributing them? This is for all those problems about allocation, assigning tasks, putting items into different containers, that sort of thing. So, to get our heads around these kinds of problems, we're going to use a really powerful classic analogy, balls and boxes. Just imagine you have k identical items, we'll call them balls, and you need to put them into n different containers, which are our boxes. And trust me, the answer you get depends entirely on the rules of the game. So, these are pretty much the 3 main flavors you're going to run into. Scenario 1, where each box can only have 1 ball at most. That's just our old friend n choose k. We're just choosing which k of the n boxes get a ball. But scenario 2 is where it gets fun. A box can hold as many balls as you want. That means a whole new trick. And scenario 3 adds a special rule about them not being next to each other. So here's the deal, and this is super important for exams. Before you even think about writing down a formula, you have to figure out which of these scenarios you're in. The number 1 mistake people make is grabbing the wrong formula because they didn't read the constraints carefully.
Okay, for that second scenario, we've got this absolutely brilliant trick up our sleeve called stars and bars. Seriously, this is a game changer. Picture it. Our K balls are the O's, or stars. Now, to split them into n different boxes, how many walls or dividers do we need? Well, just n minus one of them, right? We'll call those the bars. And just like that, the problem totally changes. Now, all we have to do is count the number of ways to arrange these K stars and n minus 1 bars in a line. We've got K plus n minus 1 total spots, and we just need to choose which K of them are going to be stars. And that is simply K plus n minus 1, choose K. You got to know this one. And hey, just a quick side note on this, if you ever need to divide stuff into more than 2 groups, say you're making 3 teams and they all have to be specific sizes, that's when you'll whip out the multinomial coefficient. It's just a bigger version of the binomial formula. That's all. Okay, on to tool number 3. This one is all about avoiding a super common trap in counting, double counting. When you're trying to count things that can belong to multiple categories at once, you need a way to deal with the overlaps without messing up your total. The tool we use for this is called the principle of inclusion-exclusion. Let's start with the easy version, just 2 sets. If you want to find the total number of things in set A or set B, you can't just add their sizes together. Think about it. If you just add them up, what happens to the stuff that's in both A and B? Yep, you've counted it twice. So the principle is super simple. Include the size of A, include the size of B, and then exclude the size of their overlap to fix your mistake. And this logic just keeps on going. For 3 sets, you can probably guess the pattern. You include the sizes of all the single sets. Then, you exclude the sizes of all the pairs. But in doing that, you've taken away the very middle part too many times, so you have to include it back in at the end. You see the pattern, right? It's always add, subtract, add, subtract. So where would you actually use this thing? A classic example is counting something called derangements. A derangement is just a shuffling of a list of things where absolutely nothing ends up back where it started. The perfect example is a Secret Santa gift exchange where no one is allowed to draw their own name. So how on earth do you count that? Well, it's a perfect job for inclusion-exclusion. You start with the whole shebang, all possible permutations, that's n factorial. Then you start subtracting out the bad cases, the ones where at least one person gets their own name. You subtract the cases where person 1 is fixed, then person 2, and so on. But then you have to add back the cases where both person 1 and 2 are fixed. See? It's that same alternating pattern again. It's such a clever application of the principle. All right, let's quickly peek into the advanced section of our toolkit. Now, you're not going to whip these out every day, but for some really specific problems, things with weird structures like trees or patterns with symmetry, these tools are absolute lifesavers. So here's a quick rundown of the heavy hitters. Catalan numbers, they show up in the weirdest places, from counting valid ways to stack parentheses to figuring out how many different binary trees you can make. Burnside's lemma is your go-to when you've got symmetry, like counting how many unique necklaces you can make from a set of beads where rotating the necklace doesn't make it new. And Cayley's formula is just wild. It gives you this stunningly simple formula, n to the n minus 2, for a really complex question. How many different labeled trees can you make with n nodes? Phew! We have covered a ton of ground. We've chosen subsets, we've distributed items, we've handled overlaps, and we even glanced at some advanced stuff. So let's pull all of this together. Let's build that final practical guide that you can use when you're staring down a tough problem on an exam. Okay, think of this as your exam time cheat sheet. It's your decision-making flowchart. You read a question. First step, what's the core task? Is it about picking a team? That's a choosing problem. Grab your binomial coefficient and just remember, order doesn't matter. Is it about giving out candy to kids? That's a distributing problem. Think balls and boxes, but for the love of math, make sure you know which of the 3 scenarios you're dealing with first. If the question has words like at least one or talks about the union of sets, that should be a huge red flag for inclusion-exclusion. And for those special cases, remember Burnside for symmetry and Cayley for labeled trees. Honestly, the single biggest mistake you can make is knowing how a tool works but using it on the wrong type of problem. So diagnosis is key. And that's a wrap. You're not just staring at a page of problems anymore. You are now a craftsperson, and you have a full toolkit at your disposal. You can look at a problem, identify its structure, select the right method, and build a solution. The only question left is, what problem are you going to tackle first?